Hello everybody. Today we'll be solving Leetcode 2577, minimum time to visit a cell on a grid. They give us a two-dimensional grid with values. They ask us to return the minimum time required in which you can visit the bottom right cell of the matrix. If you cannot visit the bottom right cell, then return -1. So we're at 0 and they want to know how long it would take to get to this cell with the 6 here. They also tell us that this upper left grid value here will always be 0. That's given. They also tell us each move you make takes 1 second. And then the question becomes, what do these 5 and 3 and 2 and 6 and 8, what do they mean? That means you can visit that cell only when the time you visit it is greater than or equal to that value. So let's go over that here. Let me go over an example really quickly. 0, 1, and 5. So for this upper left corner here, if it takes 1 second to travel to any cell, by the time we arrive at this cell here, it will be 1. So it is allowed to travel to this cell directly. If I wanted to travel to the bottom cell, by the time I arrived there, it would only have been 1 second. But this 5 indicates that 5 seconds must have elapsed for us to travel to that cell. But again, since by the time I arrived here, it's only 1 second, that means I cannot travel here directly. I would have to wait. So I want to make that clear. Let me give you another quick example. This is an edge case that I want us to take care of right now. So suppose this was the graph and these were the cells values. If I wanted to travel to the right, I could not, because by the time I arrived there, only 1 second would have elapsed. And the time must elapse must be 2 by the time I get there. Same thing for the 5. I cannot go there because by the time I arrive there, the time would only have been 1 second. So I want to take care of that edge case right now. So if g of 0 is greater than 1 and g of 1, 0 is greater than 1, then return -1. In essence, this we would be walled in or blocked in or prevented from moving anywhere if this is the case. So I wanted to take care of that edge case right now in order to make it easier, just to get us some of the coding out of the way. Okay, so let's take a pause, and I want to fast forward quickly. So let's fast forward. So let's suppose you're somewhere in the middle of the graph, of the grid. Let's suppose you're somewhere in the middle of the grid. So let's suppose you're here at this 5. So I want us to just focus on these 3 cells here. So what I'm going to do is, again, I just want us to focus here because this is what makes the problem hard. I just want to focus on this part right here. So we don't care about this stuff for now and this stuff for now. And I'm actually just going to change this to 2, and maybe I'll just change this to 3 and change this. We can leave it as 6, it's fine. So again, I just want us to focus on these 3 cells. And this is the part that makes the whole problem difficult. So I just want us to focus on this part. If we can understand this part, the rest is not or less difficult. So let's suppose we're here. We're here at the 3. So let's suppose we're here. And let's also suppose the elapsed time is 3. And we came from 2. We're at 3 now. We want to move to the 6. We want to move to the 6. So the question is, can we travel there? So if I'm here at 3 and I move to this cell 6, that means that the time would be equal to the elapsed equal to the elapsed time plus 1. In this case, that would be 4. So if 4 is less than 6, we'll need to do something. If the time is only 4, that means we can't travel to the 6 for now. But is there something we can do? So we have to move, so we'll move somewhere. We'll move to this 2 here. So let's do that. So if we're at 3, the time is 3. I move to the 2, the time will be 4. And then let's go back. Well, if I go back to the 3, the time is 5. So the time is 5 here. I can now move to the 6 because by the time I arrive there, it'll take 1 second. It'll take 1 second. So what we'll be doing here is we'll have to adjust our time to account for going back and forth. So the time will be equal to, so previously I had set the time equal to the elapsed plus 1. But I remember, since that wasn't good enough, because remember the time was only, considering that, only 4 seconds would have elapsed. But the requirement for us to visit this cell was 6 seconds must elapse. So I need to adjust our time. So the time will be equal to that 6, or so this cell value plus, and then we'll need some modification. So the time will equal the cell value, which is 6, plus some modification. So the modification will be this: 6 minus the elapsed time plus 1, and we'll mod to it. Sorry, elapsed time was a minus 1. Minus 1. Okay. So let's see what would have happened here. So if this is our modification, so it would be, let's figure this out. That would be 6 minus the elapsed time. The elapsed time is 3. 3 minus 1 is 2, so this would be 6 minus 3 minus 1 mod 2. And that gives us 6 plus 6 minus 3 is 3. 3 minus 1 is 2. 2 mod 2 is 0. So that means our time would be 6. So then that's the value that I got here, 6. Okay, so let's go over another example here. Let's just change this to, what if we have something like, suppose this is, we'll make it 9. Okay, so if we're looking at this directly, we'll have time equals elapsed time plus 1. So the elapsed time is 3. 3 plus 1 is 4. And we'll check if 4 is less than 9. And it is. That means this time isn't going to work. This time here, we need to adjust it. So we'll set time equal to that cell time. So no matter what, this cell requires a 9. That's the minimum it'll take to get there. But we'll need to check if we need to add a modification. So this is the modification we've gone with here. So this 9 is that value. I want to make sure that's clear. That this is the same 9 and 9 here, the cell value, minus the elapsed time. The elapsed time is 3, minus 1 mod 2. And so let's look at this here. So 9 minus 3 is 6. 6 minus 1 is 5. 5 mod 2 is 1. So this would be time equals 9 plus 1, which equals 10. Okay, so let's see if that's accurate. So if we're at 3 here, if I travel to this 9, that would only take 1 second, which is 4. That's not going to work. So we'll have to perform this back and forth type of action. So I'm at 3. Let's go back to the 2, which would put us at 4 seconds. Back to the 3, which is 5 seconds. That's still less than the 9. It's not going to work. So let's go back to the 2 and back to the 3. If it's at 7 seconds and I'm at 3, by the time I arrive at 9, that'll only give us 8 seconds. So I need to go back to the 2 and back to the 3. Now the time is 9 seconds. By the time I travel to the 9, it'll be 10 seconds. 10 seconds. And that's what I got here. And that's what I got here. So this is what we want to do here. We want to, when we're adding our values to the queue, we want to be using this type of calculation to figure out what values to use. All right, so let's kind of code it up together. So when we're using Dijkstra algorithm, we'll be using a heap, and in our heap, or I'll just, in essence, a priority queue. We'll be storing 3 values: the time, the row, and the column. So let's go over that really quickly. Well, first let's figure out the rows and dimensions of the grid. Okay. And then we'll create our queue. So our queue will hold these values here: the elapsed time, the row, and the column. And we'll be sorting this queue based on the elapsed time. In essence, a min heap. So let's go over that. So the very first cell, they tell us that the time is 0 and the row is 0 and the column is 0. So we know that. In order for us to check the directions of each cell, we'll create a constant to store the deltas of the directions. Okay. And then in order to prevent us from visiting the same cell twice, we'll use a 2-dimensional grid. So 0 will mean it's not visited, and a 1 will be it has been visited. We'll indicate. And for now, we'll just set that first value equal to true, meaning it has been visited. Okay, so for Dijkstra's, we'll just keep looping through our queue here until it's empty. So we'll pop off the first value of the queue, which is the minimum. And remember, the 3 values I've placed onto each node within the queue are the elapsed time, row, and column. So we can put that here. We'll just call this time, row, column. And now let's loop through all of the directions to find the valid neighbors. So these are the delta r's, and so we'll calculate the new row with the current row plus the delta r. Same thing for the column. And now we'll want to check if this row and column are valid entries are within the grid dimensions. So we want to make sure the row value is greater than or equal to 0 and less than the number of rows. And what else? Well, we don't want to visit a cell twice, so let's check if this cell has not been visited and not. Okay, so that means we're allowed to visit the cell because we have not visited it before. Now let's go back to this calculation that we did up here. So we'll be using this idea to figure out what value to place for this elapsed time on our queue. Okay, so our new time will equal the current time plus 1. Now remember, we check if this time is, if it's less than this value, remember we need to modify it. So let's modify it. So t equals, so we're going to set it to that value, but then we'll need to add some like modification if necessary. So let's check that out. So remember what we did before, we compared it to that value, the cell value, minus the elapsed time plus 1, which is just t here. And we modded by 2. Okay? And that's it. That's the value we'll be adding to the queue. Now, what we should do though is we can check if this row and column are our goal. So if row column equals row minus 1 column minus 1, if this is our goal, our destination, then we can return this time, and that would be our answer. Otherwise, we'll add this new node to a queue, to our queue here. So heap push queue and trc. And don't forget to update our visited. So visited rc equals 1. And I think this should be fine. I think this is it. So again, I wanted to point out this part was the hard part here. Let's just check it, see if this works. Okay, looks good. Let's submit it. Okay, looks pretty good. All right. Yeah, I think this problem was difficult, and it was maybe even difficult for me to explain. If you find this video helpful or educational, give a like. Other than that, have a great day. Take care.